Hey guys, and welcome to this video on solving systems of equations using linear combinations, also known as the elimination method. So let's get right to it. All right, consider the system of equations 3x minus 4y equals -1 and -3x plus 10y equals 4. Now, our first strategy for solving systems of equations was to graph the two. But if we put these in y equals form, neither of these look very appetizing to graph. They have fractions for y-intercepts and fractions for slopes. I feel like I might have to do some eyeballing or estimation, and if our graphs aren't really accurate, we might not get the right solution. Maybe we can try doing substitution. Obviously, solving for y in either of these equations is not going to be very fruitful. Maybe solving for x will be. Unfortunately, solving for x doesn't help us much either. We got a whole bunch of fractions. And of course, we can still use the substitution method when we have fractions, but it'll just be a little bit more tedious and a little bit harder. So I'm wondering, could there be an easier way to solve this system of equations than by graphing or substitution? All right, again, let's assume that there is some ordered pair x, y that is a solution to this system of equations. So we're going to assume that both of these equations are true. Now, one thing that I want to point out right away is that we happen to have a 3x in our first equation and a -3x in our second equation. And we're going to use the fact that if we were to ever add 3x and -3x, they would add to 0. All right, now let's just focus on the first equation. We know that if we're ever given an equation, we can add the same number to both sides of the equation, and that's okay. We'll get another true statement. So we're going to do just that, but in a very tricky way. Let's look at the second equation. We know that -3x plus 10y equals 4. That is, -3x plus 10y and 4 are the exact same thing. They're equal to one another. So what we're going to do is we're going to take this first equation and we're going to add 4 to the right-hand side, and we're going to add 4 to the left-hand side. On the right-hand side, we're going to add the number 4. And on the left-hand side, we're also going to add 4. But instead of actually adding the number 4, we're going to add something that's absolutely the same thing as 4. Something that's equal to 4. We're going to add -3x plus 10y. And when we do that, we're going to end up with another true equation. And what's so great is that when we add 3x and -3x, that's going to give us 0. So what do we end up with? 6y equals 3. We've successfully eliminated the variable x from our equations and ended up with an equation involving just one variable. And this is no problem to solve. All we gotta do is divide both sides of the equation by 6. And so we find that if there is a solution to this system of equations, if both of these equations are true at the same time, then it must be the case that the y-coordinate is 1/2. And once we find the y-coordinate, all we gotta do is substitute that into either of our original equations and find the x-coordinate. So we find that the solution to our system of equations is the ordered pair 1/3, 1/2. All right, let's try another. Now let's try to solve the system of equations 4m plus 7k equals 20 and 5m equals 7k minus 38. So just looking at both, I can tell right away that it's going to be really tough to graph these without doing some eyeballing on the graphing part, because there's going to be a lot of fractions whether or not we solve for m or for k. Equivalently, because solving for m or k is going to involve a lot of fractions, using the substitution method might be a little bit tedious. So again, perhaps we could try a strategy similar to the one we did last time. First though, it'd be really nice to have all of our m's and k's in nice columns. So let's rearrange this second equation. Note, if we ever choose to solve a system of equations using this strategy, that is, using what's called linear combinations or elimination, it's probably best to put each of our equations in the form ax plus by equals c, where a, b, and c are all numbers, and x and y represent whatever two variables we're working with. And you can see that this equation and this equation are in that form. It's just really nice to have our variables in nice columns. Well, take a look. It looks like we have a 7k in one of our equations and a -7k in the other. If we could somehow add those together, they would add to 0, which would be really nice because maybe we could come up with an equation involving just one variable, namely k. So once again, we're going to assume that there's an ordered pair, m comma k, that makes both of these equations true at the same time. So that is, we're going to assume that both of these are true. So let's look at this equation right here. 5m minus 7k equals negative 38. Of course, if we add the same number to both sides of the equation, we're going to get a true statement. And that's exactly what we're going to do, but in a very tricky way. We're going to add 20 to both sides of this equation. On the right-hand side, we're going to actually add the number 20. On the left-hand side, we're also going to add 20, but we're not going to actually add the number 20. We're going to add something that's exactly equal to 20, namely 4m plus 7k. And when we do that, we end up with this really nice equation, 9m equals negative 18. And I'm sure we can solve that. So, if there's a solution, if both of these equations are true at the same time, then it must be the case that the m value is negative 2. And now that we've got the m value, we can substitute that into either of our equations to find the k value. And so we find the k value to be 4, and the solution to this system of equations is the ordered pair negative 2 comma 4. Alright, let's try a slightly trickier system. Now let's try to solve the system 3w minus 5d equals 16, and 6w minus 4d equals 2. Again, if we try to solve for either of these variables, we're going to have a lot of fractions going on. So graphing or substitution are going to be pretty tedious and or inaccurate. So we might have to use this linear combinations method again. Now unfortunately, we don't have any terms that are going to immediately add to 0 like last time. If we did, we'd be ready to add and everything would be groovy. Now let's just take a look at the 3w and the 6w for a moment. If this 3w were a negative 6w, we'd be home free, but we don't have one. Now is there anything we could do to make that 3w a negative 6w? Well, let's look at our first equation. We know that given an equation, we are allowed to multiply both sides of that equation by the same number, and we'll get another true statement. Well, if we multiply both sides of this top equation by negative 2, then we'll have a negative 6w in this equation and a positive 6w in the other. So now I think we're ready to make some moves. Let's take this first equation, negative 6w plus 10d equals negative 32, and let's add 2 to both sides of it. On the right-hand side, let's actually add the number 2. On the left-hand side, let's add something that's absolutely equal to 2, namely 6w minus 4d. And so we find that if there's a solution to this system of equations, the d coordinate has to be negative 5. And now we're ready to just substitute that value in for d in any of our equations and find the value of w. And so we find our solution to this system of equations to be the ordered pair negative 5 comma negative 3. Now note, we could have multiplied that top equation by something slightly different. We could have multiplied it by 2. And if we did that, we would have a 6w in one equation and a 6w in the other. So adding the 2 would not yield a 0, but subtracting 6w from 6w would give a 0. So in this case, we'd have to subtract 2 from both sides of the equation. On the right-hand side, of course, we'd actually subtract the number 2. And on the left-hand side, we'd subtract something that's absolutely equal to 2, namely 6w minus 4d. Now we got to be really, really careful if we do this, because writing just this would actually not be appropriate. We're subtracting the whole quantity, 6w minus 4d. So when you're using subtraction, now you got to worry about double negatives and stuff. So in my opinion, it's a lot harder to keep track of things and a lot more likely that we make a mistake. But If you're able to keep track of them, you'll be just fine. And of course, you end up with the same d value and therefore the same w value and the same solution. But in general, I would multiply the equation by whatever you need to so that you can add in the future, because when you have to subtract, you might make a mistake. All right, here's another tricky one. On first inspection, it's clear that solving for x or y in either of these equations is going to yield some nasty fractions, so it looks like we want to use this linear combinations method. And once we decide that, let's go ahead and put both of these equations into a form where all of our x's and y's are in nice columns right above each other. All right, unfortunately, we don't have any terms that, when we add them to each other, will give 0 right away. But I'm looking at this negative 4y in our first equation and this 8y in our second. If we multiply both sides of this first equation by 2, we'll get a negative 8y. And then if we add negative 8y to 8y, we'll get 0. So let's multiply both sides of this first equation by 2. All right, now we've got the equation 6x minus 8y equals negative 18. Let's add 51 to both sides of that equation. On the right-hand side, we're going to actually add the number 51. And on the left-hand side, we're going to add something that's equal to 51, namely 5x plus 8y. So we find that the x value of our solution is going to have to be 3, and to find the y value, all we need to do is substitute 3 into any one of our equations and solve for y. And so we find the y value of our solution to be 4.5, and so our solution is the ordered pair 3, 4.5. All right, here's an even tougher example. Of course, after a quick glance, you can tell that solving for x or solving for y is going to yield a lot of fractions, so it's not going to be easy to graph, and it's not going to be easy to use the substitution method. So let's use the linear combinations method. We've got our x's and y's already in nice columns, so that's great. Now, I'm looking, and there are no gimme terms here. It would be great if we had a positive 4x and a negative 4x, or a negative 7y and a positive 7y, but we don't have that. And not only that, it's impossible to manufacture one of those pairs that add to 0 by multiplying just one of our equations by a number. So this is going to be a lot more challenging. All right, let's start by looking at the terms with the x in them. I know that it's possible to get 20 out of both 4 and 5. It's their least common multiple. So if we were to multiply the first equation by negative 5, this would become a negative 20x. And if we multiply the second equation by 4, that would become a positive 20x. And then we'd have two terms that would add to 0. So let's go ahead and multiply the first equation by negative 5 and the second equation by 4. All right, so we've got this negative 20x and this positive 20x. And we know that if we add the two together, we're going to get 0, which is great. So we're going to take our first equation and we're going to add negative 60 to both sides of it. On the right-hand side, we're going to actually add the number negative 60. On the left-hand side, we're going to add something that's equal to negative 60, namely 20x minus 28y. Now, I want to show you a little shorthand that some people use to take care of these problems. A shorthand way to tell the reader that you're adding negative 60 to both sides of the equation without actually adding the exact number negative 60 to both sides is to simply write the two equations as they are and toss a plus right here. And that means we're adding 20x minus 28y to the left-hand side of the equation and negative 60 to the right-hand side, and that this is okay because the two are equal to one another. And in this case, we end up with and we find that our solution to this system of equations is the ordered pair 4, 5. Now note that when we first did this problem, we decided to multiply the first and second equations by numbers so that we'd be able to eliminate the x's and obtain an equation involving just y's. But there's no reason that we couldn't have multiplied them so that we'd eliminate the y's and end up with an equation involving just x's. So let's look at the terms involving just y's in this case. Well, I know that 5 and 7 both go into 35, their least common multiple. So if we were to multiply this top equation by 7 and the bottom equation by 5, we'd end up with a positive 35y in our top equation and a negative 35y in our bottom, and we'd be good to go. So let's do just that. All right, so let's take this top equation and let's add negative 75 to both sides of it. On the right-hand side, we're going to actually add the number negative 75. And on the left-hand side, we're going to add something that's exactly equal to negative 75, namely 25x minus 35y. And the shorthanded way of writing that is just to put a plus sign next to that second equation. And that tells the reader that you're adding the same number to both sides of the equation, but on the right-hand side, you're actually just adding the numeral negative 75. And on the left-hand side, you're adding 25x minus 35y. And what we end up with is we find our x value to be 4. And of course, if we were to substitute that 4 into any one of our other equations, we'd find the y value. And of course, we end up with the same y value, and therefore the same solution. Alright, it's about time that we get some practice. So why don't you try solving the system of equations 4w minus 6k equals negative 2, and 6w minus 7k equals negative 7. Now there are tons of different ways to go about this. You could try to eliminate the w's, you could try to eliminate the k's. So what I'm going to do is I'm going to solve this twice. In the top system, I'm going to go about it by eliminating the w's, and in the bottom system, I'm going to go about it by eliminating the k's. I mean, hopefully the equation we get should be the same for both, but I urge you to do it in whatever way you'd like. So why don't you pause the video and take care of it, and when you're done, play the video and we'll reconvene. Alright, last two examples. Why don't you just go ahead and pause the video, and please try to solve both of these systems of equations, and when you're done, play the video, and we'll see how it went. Alright guys, that's it for this video. I hope you found it helpful, and I hope you enjoyed.